All right, how's it going, everybody? So I am pre-recording a video today for our lecture for Thursday, February 24th. What I'm going to do is kind of lecture as much as I can. I know that video lectures with no feedback, the timing is a little bit off, so I probably won't go 75 minutes, but I want to lecture a little bit, and then if there's any gaps or anything that needs to be filled in, I actually have some old videos. I don't like using those unless I absolutely have to, but if we have to, we have to. So just a few administrative things. I know that most of you took the exam in person in class on Tuesday. Some of you had a makeup exam scheduled for various reasons on Thursday. There was a large, I think about half the class actually had like a makeup or something like that. And so if you have a scheduled exam to be made up that was going to be done on Thursday, you'll just have to call back to the Disability Access Center. Or you'll have to call back to the, what am I saying? The testing center, and then schedule that with them again. And I'll have to just extend the date. So I don't think I'll get the exams back on Tuesday next week. I try and get them back within a week. But I think with that one missed day, I just have to give a few other people some extra time. So that'll be what it is. So that's that. And then also there's no homework due on Monday because we haven't talked about anything yet. So I may give you a few things just to practice, just to work on, but I'm not going to collect any homework on Monday night. Just because it's been a weird couple of weeks with the snow day last week and then snow day today. So there we are. So what I want to do is I want to continue talking about number theory. So I know that it's been scattered what we've been talking about, but I want to continue to talk about number theory. And then let's just jump right in. So I want to talk about what's called Bézout's little theorem. Okay, Bézout is Étienne Bézout is a French mathematician. There's a Bézout's theorem in algebraic geometry. That's definitely not what we're talking about. But we're just talking about Bézout's little theorem, which says that if you have two integers, a and b, and those integers are relatively prime, then there exist integers x and y, so that you can write 1, in other words, the GCD is a linear combination of a and b. So you can write 1 as ax plus by. This theorem does not tell you how to find them. I will today walk through how to construct the integers x and y. So there's a nice constructive proof. But before we do that, I want to give you what I think is a really nice proof that fills in a lot of the details. So we'll talk about a way that we can actually explicitly construct x and y. X and y are often called Bézout coefficients. But before we do that, let's actually talk about the proof about why you can always find such an x and a y. And so the idea is I want to consider the set S, and S is going to be the set of integers of the form ax plus by, where let's see, x and y are integers, and ax plus by is positive. Okay, so this is the set of all positive linear combinations of a and b. And what we're going to do is I'm going to let D, this is a subset of the positive integers, and therefore by the well-ordering axiom, it has to have a smallest element. I'll call that element D. So let D be the minimum value of S. Okay, and what I want to do is I want to show you that actually D divides our goal. Let me just write that. Our goal is to show that D divides A and D divides B. And if you think about what S is, if S is a bunch of positive integers, if D is in the set, so D is a positive integer, and if D divides A and D divides B, and if A and B are relatively prime, then there's only one option left. D has to be 1. Okay, and so yeah, so this will show that 1 is the smallest value in this set. In other words, 1 is equal to x plus by for some x and y. So that's our goal. That's our strategy. So D is the minimum of the set S. And what that means is that we can write D. So we can write D as A, let's call it X naught plus B times Y naught for some values, X naught and Y naught in Z. Okay, so if D is in the set, we can write D as some value like that. And then what I want to do is I want to apply the division algorithm to A and D. And so let's let A be written as DQ plus R by the division algorithm. And so what I mean by that is that I'm going to take A and divide it by D. R is going to be the remainder that we get. Okay, where here R is going to be some number that's strictly less than D, or less than or equal to D minus 1, however I want to say. Okay, and so that's the first part. Now, notice that R, so notice that R is A minus DQ, just by the fact that A is DQ plus R. So that's silly, but R is A minus DQ. And D has the special form. D is A X naught plus B Y naught times Q. And so if you collect all of these terms, you can write this as A times, let's see, 1 minus Q X naught, and then plus B times minus Q Y naught. Okay, and hopefully I did the algebra right there. But the point is that R can be written as a linear combination of A and B. In other words, R is either in this set or, so R is either in this set or R is 0. Okay, and we have to decide which one. Now I know that R is going to be greater than or equal to 0 because it's a remainder, and we applied the division algorithm. So I know R has to be greater than or equal to 0. The problem is that, well, it's not a problem, but if R was positive, then R would be in this set, and R is less than D. But remember, we let D be the minimum. So since R is less than D, and D is the minimum, we only have the choice that R is equal to 0. And if R is equal to 0, it follows that A is equal to DQ. So D divides A. Okay, and so A is equal to DQ plus R, but R is 0. So that means D must divide A. And likewise, we can play the same game. So likewise, D divides B. Okay, and therefore, for the reasons that we talked about at the top of the proof, D equals 1. All right, so that's the proof there. So 1 is the smallest value that you can write as a positive linear combination of A and B. Okay. The proof actually tells us a little bit more than I claim. If the proof actually says that if D, let me write it like this. The proof actually says, I was going to write it a little bit more complicated, but the proof actually says that the greatest common divisor of A and B is a linear combination of A and B, and it's the smallest positive one. Okay, so it's the smallest positive integer that can be written as a linear combination of A and B. So for example, if I were to have 2 even numbers, then every linear combination of A and B would also be even, because if they're both even, then from all the stuff that we know about evenness, you could factor 2 out on this side. And so 2 would be the smallest thing that you could write as a linear combination. You certainly couldn't write 1 as a linear combination of 2 even numbers, because you could always factor out a 2. Okay, and so you can play these same games, but the greatest common divisor is the smallest positive integer that's a linear combination of these 2 numbers. Okay, so that's essentially what we proved. but we really only need to write down the formal proof or write down the formal statement when A and B are relatively prime. Okay, so that's what we're going to use it for now. Okay, so that's the statement. So Bézout's little theorem, despite being simple to state and relatively simple to prove, is actually very useful. And one of the reasons where, one of the places where it comes up is what's called Fermat's little theorem. Again, there's a Fermat's big theorem. It's actually called Fermat's last theorem, also about algebraic geometry, coincidentally. But Fermat's little theorem is about modular arithmetic or primes, however you want to think about it. And what Fermat's little theorem says is that if P is prime, and if P divides a product, A and B, then P divides A or P divides B. In other words, if you were to take a prime and a prime divides a product, the only way that can happen is if the prime goes into one of the terms of the product. You can't take the prime and split it into pieces where one piece divides A and one piece divides B. You can't do that because primes they don't have pieces, right? They're not composite, they're just primes. So if you were to have, this is not true, of course, if you pick anything that's, this is not true, for example, for composites. In general. So if you were to pick, say, 6, 6 divides 12, but obviously 6 does not divide 3 and 6 does not divide 4. So there's a way that you can kind of take 6 and then split it into pieces so that one piece divides 3 and one piece divides 4. Okay, primes, you can't do that. So let's prove this. First, if P divides A, we win. Okay, so if P divides A, then the statement is true. Okay. So the statement holds. If P does not divide A, then if you think about that for a second, A and P have to be relatively prime. Okay, so if P does not divide A, then A and P are relatively prime because A can't divide P, right? A and P can't have any primes in common unless A is a multiple of P, just by the definition of a prime. And therefore, if A and P are relatively prime, by Bézout's little theorem, what we can do is we can find values X and Y so that 1 is equal to AX plus PY. Okay, so 1 is equal to AX plus P. I wrote B, but I meant P. Y. Okay, and then what we're going to do is we're going to multiply both sides by B. So it follows that B is equal to BAX plus BPY. And by assumption, P divides AB. So in other words, there exists a value K where AB is equal to PK. And therefore, if I take this equation, B is equal to BAX plus BPY, it follows that B is equal to BAX plus PBY. Okay, where I replaced AB with PK. And the point here is that you can factor P out of the right side. So this right side is P times KX plus BY, and therefore P divides B. So there's something very, very useful about Bézout's little theorem in that it kind of cuts to the heart of all of these division statements. Okay, so it'll be very useful for us going forward. Okay, so P is prime and P divides a product, then P divides A or P divides B. You can extend this just a little bit if you want. So I'll just call this a proposition. If, say, A and C are relatively prime and C divides AB, then C divides B. Okay, and I'll leave the proof as an exercise. When I say exercise, I mean just try and prove it on your own. I'm not going to collect it. Okay, unless I assign it as a homework. But anyways, so that is Fermat's little theorem. So what I want to turn to now is I want to turn to studying what are called linear congruences. And so with linear congruences, what I want to do is I want to study, I want to find values x so that ax is congruent to 1 mod m. Okay, so we want to find values x so that ax is congruent to 1 mod m. And what I really want to prove, is that ax is congruent to 1 mod m has a unique solution. So this will have a unique solution if and only if a and m are relatively prime. By a solution, by the way, what I mean is a is going to be some number. Let me look at an example here. So let's look at 3x is congruent to 1 mod 7. And so what that means, when I say unique, I mean mod m. So what I want to do is I want to think about the numbers 0 through 6. And I know that since 3 and 7 are relatively prime, I'll prove this proposition in a bit, but let's assume it's true for now. Since 3 and 7 are relatively prime, there must be a solution x that satisfies this. And it turns out if you take 5 and plug it in, 5 works. So 3 times 5 is 15. 15 is a multiple of 7 plus 1, so it's congruent to 1 mod 7. Okay, so you can just check that x congruent to 5 mod 7 is a solution. Okay, and that's the only solution mod 7. So the uniqueness that we got is mod m. Okay, there's only one value from 0 to m minus 1. And so that's what I want to do. I want to kind of build towards how did I come up with 5? I mean, this example is small enough. We could just try a few values and see what happens. But I want to be a little bit more systematic. And this is the kind of math that actually gets used a lot in cryptography. Okay, so there's some stuff here that we'll talk about. All right. So before we get to actually proving this, before we get to solving linear congruences, what we need to get good at is using what's called the Euclidean algorithm. So there's the Euclidean algorithm. And what this is it's an algorithm, it's a method for us to compute quickly and efficiently the GCD of two numbers. So this allows us to compute the GCD of A and B very quickly. Okay, it's a very efficient algorithm. And the idea is basically just use the division algorithm over and over. And then we'll show you how this works. What I want to do is let's actually do an example. I'll show you how this algorithm works, and then I'll prove why that works. And then we'll write down the algorithm in general. But let's say I wanted to compute the GCD of 24 and say 13. Let's say 24 and 7. Okay, obviously the GCD is 1, but the important point here is how this process actually works. So let's say I want to compute this GCD. What I'm going to do is I'm going to take 24 and I'm going to apply the division algorithm. So I'm going to think about how many times does 7 go into 24? Well, it goes in 3 times with remainder 3. Okay, and then what I'm going to do is I'm going to take the divisor in the remainder, and I'm going to do this again. So let's think about how many times 3 goes into 7. Well, it goes in twice with remainder 1. And then I'm going to take the divisor in the remainder and do it again. How many times does 1 go into 3? Well, it goes in 3 times with remainder 0. Okay, so that last one's kind of silly. And then we stop. And it turns out that the second to last remainder, in other words, the last non-zero remainder, which in this case was 1, that's our GCD. So the GCD of 24 and 7 is 1, which again, we already knew. 7's prime, 24 is not a multiple of 7, so the GCD is 1. So what I want to do is kind of explain why this process works, explain how the algorithm works, why it's a particularly efficient algorithm, and then we'll do some examples, and then we'll see what this has to do with linear congruences. Okay, so that's the master plan here. So the first thing, and I'll just call this a proposition. So the first thing here is, let's say that I have numbers a, and a is equal to bc plus d. Okay, let's just assume everything is positive. I don't really want to talk about the GCDs of negative numbers. They're not hard. They're annoying. So I don't really want to worry about that. I mean, the divisors of a negative number are the same as the divisors of a positive number, so we don't gain anything. I just don't want to deal with those. So let's assume that we write a as bc plus d. I am not assuming necessarily that we're applying the division algorithm here. So I don't care if d is a true remainder. I just want to prove that if a is equal to bc plus d, then it turns out that the greatest common divisor of a and b is the same as the greatest common divisor of b and d. Okay, that last part. And so the reason why the division algorithm works is that the GCD of 24 and 7 by this line of reasoning is the same as the GCD of 7 and 3. And that's the same as the GCD of 3 and 1, which is 1. Okay, that's really the line of reasoning here, is that we can kind of simplify this each step along the way. Okay, and so let's talk about the proof here. And let's let S sub AB be the set of common divisors of A and B. So it's all the positive, let's say positive integers that divide A and divide B. So for example, if I were to have S 12 and 20, what are all the common divisors of 12 and 20? Well, 1, of course, 2, they're both even, 3 is not in there, 4, and I think that's it. Okay, so S12, 20 is 1, 2, and 4. So those are the only positive divisors of both 12 and 20. So that's what I mean when I write this S sub AB. So I'll just leave that off to the side here, or maybe I'll leave that up in the corner. Okay, so what I'm going to do with that is I want to look at this SAB, and what I want to just point out is that we'll show that S sub AB is the same as the set of SBD. And so the point here is that not only do A and B and D have the same greatest common divisor, actually all their divisors are the same. And that's a little bit more than what we wanted here. Okay, so let's let T be an SAB so that T divides A and T divides B. One of the facts that we proved early on in this chapter is that if T divides two numbers, then it divides every linear combination of those two numbers. Okay, so if T divides A and T divides B, then T divides A minus BC, because it divides every linear combination. I mean, in fact, T divides AX plus BY for all integers X and Y. But in particular, T divides A minus BC. And the reason why I care about that is that that shows T divides D. Okay, and if T divides D, well, by assumption, T divides B, so T is in the set of common divisors of B and D. And that actually already gives us the first set containment. The other direction's just as simple. If it's actually even simpler, if T divides B and D, so T divides B and T divides D, then T divides every linear combination of B and D, and in particular, T divides B, C plus D. So T divides A, okay? And so A and B, whatever their set of common divisors, that's the same as the set of common divisors of B and D, okay? And so that's enough to prove that since these sets are the same, their GCDs are the same. The greatest divisors are also the same. Okay, so that's the idea. And then once you apply this idea to the division algorithm, I want to kind of explain why this algorithm works. If you care about algorithms at all, you know that you want to talk about proving that the algorithm stops at a certain point. And here, if we repeatedly apply the division algorithm, notice that the remainders have no choice but to keep getting smaller. Because if I take 24 and divide by 7, I get a remainder of 3. I've got to get something between 0 and 6. And if I divide by 3, I have to get a remainder of 0, 1, or 2. It's got to be smaller than 3. And if I divide by 1, then of course I get a remainder 0. There's no other option there. Okay, so since the remainders keep getting smaller, this process has to stop at some point, and there we are. Okay, so that's the proof there. What I really want to do with this is, this is a nice, efficient way for us to compute GCDs, but the main utility of this result, the main utility of actually looking at, when I say this result, I mean the Euclidean algorithm, is you can use the Euclidean algorithm to construct Bézout coefficients. So that's what I really want to do. So let me show you how that works. So let's say I want to find the Bézout coefficients of 24 and 7. In other words, I want to find values so that 24x plus 7y is equal to 1. And it turns out there's infinitely many values that work. We just want to find one such pair. Okay, what we can do is we can use the division algorithm. And so let me copy the division algorithm here. In fact, let me just redo it because it's so short. But we said 24 is 7 times 3 plus 3. 7 is 3 times 2 plus 1. And then actually we can stop. We don't need the last line. But the idea is that I'm going to take the remainder here, take the remainder 1. And so we can write 1 as 7 minus 3 times 2. Okay, and then once we use that information, we can be done with that. And then in the next step, I'm going to notice that if I solve this equation for 3, this equation says 3 is equal to 24 minus 7 times 3. So I'm going to replace the 3 here with 24 minus 7 times 3. And then that's all times 2. And I want to keep the 24s and the 7s intact. So when I distribute the 2, I'm going to get 2 times 24 minus, it's actually plus 6 times 7. Okay, it's plus because we have a minus and a minus. So this 2 times 3 is 6. And then it's plus 6 because we have the 2 negatives. And then if I add 7 plus 6 times 7, I get 1 is equal to 7 times 7 minus 2 times 24. And so one example of Bézout coefficients here would be x equals 2, x equals negative 2 and y equals 7. So we can take x equals negative 2 and y equals 7. Okay, and that's going to be very useful for us. And we'll talk about soon, maybe next time, we'll talk about how to use this to solve linear congruences. I don't want this video to get too long here. It's already a little bit longer than I was hoping. So let's do another example of finding Bézout coefficients. And then next week, that'll be Tuesday, March 1st, we'll talk about how to actually use these Bézout coefficients to find, to solve linear congruences. Okay, I'll explain more there. So let's look at, say, 213. Okay, so let's say that those are two numbers. And what I want to do is I want to compute the Bézout coefficients. I want to compute the Bézout coefficients of 213. In other words, I want to write 1, which is their GCD, as a linear combination of 213. I know that 200 is not a multiple of 13. You can just check that it's not a multiple of 13. And yeah, since 13 is prime, that means that 13 and 200 are relatively prime. So 1 is their GCD, and we can find Bézout coefficients and everything is fine. So what I want to do is let's apply the division algorithm. So 200 is going to be 13 times, let's see, how many times does 13 go into 200? So 13 times 13 is going to be 169. So that's 31, which means that I think 15 times 13 will go into 200. 13 times 15, you get the joy of, I would do this in class too, but multiplying. So we get 150 and 45, so that's 195. So 200 is 13 times 15 plus 5. So that's 195, okay? And let's see, then we do the same thing with 13 and 5. 5 goes into 13 twice, with the remainder 3. Okay, and then we play the same game. 3 goes into 5 once, with remainder 2, and then 2 goes into 3 once, with remainder 1. And then notice again that the remainders keep getting smaller, 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 smaller. Okay, because every time that we divide by a smaller and smaller number, we have to have a remainder that gets strictly smaller than our divisor. Okay, and so what we can do now is we can walk backwards through this process and find the Bézout coefficients. So we're going to start with our last equation, and that's 1 is equal to 3 minus 2. Okay, and then I like to cross off the equation once we've used it. And then we're going to solve the next up equation, the one that's just above it. We're going to solve it for the remainder. So 2 is 5 minus 3. And so that means that we've written 1 is 2 times 3 minus 5. So everything is fine so far. And then we've used that equation. And then 3 is 13 minus 5 times 2. So now we're writing 1 as a linear combination of 13 and 5. And when we distribute everything, we're going to get 1 is, let's see, 2 times 13. And 2 times negative 2 will be negative 4 times 5 minus 5. So negative 5 times 5. And that checks out because 2 times 13 is 26. 5 times 5 is 25. So that's good. So now you've written 1 is a linear combination of 13 and 5. And this example, and we use that 3 is 13 minus 5 times 2. This example, I want to point out, there's one quirk that happens here. And it's not even a quirk. It's just we need to kind of decide what do we do here. The next GCD that we're going to solve, and the last one here, is 5. And what I'm going to do is I'm just going to replace one of the 5s, okay, with 200 minus 13 times 5. So we're going to get 5 times, let's say, 200 minus 13 times 5. And so if we multiply everything, we're going to get 1 is, let's see, 2 times 13. So we're going to get here minus 5 times minus 5 will be plus 25, plus 2 I'm doing too much here all at once. Let me write one more step. So we got 1 is equal to 27 times 13 minus 5 times 200. And just because I don't trust my arithmetic, and because this is going to be written down for forever, YouTube or whatever, let's see. So we have 27 times 13 is 350. So I made a mistake somewhere. So let's see, where did I make a mistake? We said 5 was 200 minus 13 times 5. I made a mistake. This should be a 15. 5 is 200 minus 13 times 15. And that changes things. So that means that wasn't 5 times 5, that was 5 times 15. So that's a 75. And then altogether 77. I'm glad I checked. And let's see, 77 times 13 is 1001 minus 5 times 200 is 1000. So there we go. So that's perfect. So these are the Bézout coefficients. So we get 77 and minus 5. So again, if we want to write 1 is a linear combination of 213. One example, kind of the smallest example, would be x is minus 5 and y is 77. These are numbers, I mean, these are not numbers that are super big, but these are numbers that are, I think, big enough that we would have trouble coming up with these examples on our own, okay, without actually calculating this. I think it's probably this is the first example of two numbers that are big enough where we can't compute the Bézout coefficients just by kind of thinking of it. We have to write it down and do a little bit of work there. So I think that's a good place to leave it for today. What I would like you to do over the weekend is to, I'll leave a little bit of stuff that I'd like you to do. There might be a few other videos that I want you to do, maybe a few kind of practice problems, but I'm not going to write anything down or ask you to turn anything in with homework. I think what I'll do is I'm going to come up with kind of a worksheet for maybe some practice problems, and then we can talk about it on Tuesday, or I'll write down solutions or something like that. Okay, so I hope everyone has a nice snow day, and I look forward to seeing you all next week, Tuesday, March 1st. All right, take care.